Okay, so then I want to talk about the duality and of the lens shape, and TN. So if you have a lens cone of the RPN, then you can take the dual and then obtain some lens of the P and neighborhood, which is in the one side. Okay, so basically recall the duality map. So you have some O tilde and O tilde star. So you have a dual manifold, and if you look at the p ends of these, and then there's a groups are also there's a dual relationship between the ends because of the Bimberg duality diffeomorphism. So it give you one-to-one correspondence between the p ends. Okay. So we recall this augmented boundary, which is so take boundary point, but you also consider the sharply supporting hypersphere contain h of the omega. So this is a cross surface, subspace, and then the so these are all oriented things, and then so you duality map is just that you switch x and h because so if you look at the these omega star, then the role is actually switched. Okay, so and then this is of course diffeomorphism, and the inverse is just itself, right? And so on. Okay, and so for example, if you look at something like this with a cone, then these supporting lines will actually go to points in here, and then everything supporting at B actually goes to some plane here, some convex subset of the plane. And of course, we call these projection maps. So you forget the hyperspace, you just remember the point. That's what should happen. And so if you have some thing like the lens cone, then and then suppose there's some upper boundary component of the boundary, which is called A, and it has a property that for each segment from this vertex to each point of this boundary of A, it's actually tangent. Okay, and then it has the same property. Then this property, then join is the same as that of L. Then so the dual domain will be some crossover component of some lens with the hyperplane passing through it. And A corresponds to some hypersurface in one of the boundary, and A union D is a boundary of L1 for some totally geodesic n-1 plane domain D due to this RB part. Okay. So RB part is the set of rays from V to V star L, and D is given by some difficult formula, but I don't want to explain. So this is essentially captured here. So if you have a cone, then these set of hyperplanes actually now becomes points on this convex domain, and the A is now goes to this A prime, and it's actually tangent, has to be tangent here. Okay, so that's and conversely, if you have a lens L and then it meeting the L0, and then it has this component has strictly convex boundary with the boundary in P. Then the dual is actually some kind of a lens cone, and it has all these property like the above. Okay, so you have something like lens, and then you cut it off the top part, then it will get dual to something like this. Okay, so that's proof is a fairly long thing. You just need to walk through this. Okay, and right. So for example, if you want to, so there are segments from B to the boundary of A. So they correspond to parameters of hyperplanes at some points here. So these are what you call the tensor. So in projective geometry, tensor means just one parameter family of projective subspaces satisfying certain conditions. Okay. Of course, the algebraic geometry use the same term, but maybe in different sense. But here, so you look at the ones which contain some hyperplane. In this plane, there's some supporting hyperplane. So you consider all the hyperplane containing that, and that corresponds to one segment. So there's some hyperplanes containing a hyperplane here with respect to this one, and then that gives you a plane. So for each point and hyperplane, you get a segment like this. So those are the basic idea here. The proof. So duality of T and then the properly convex Rn. So you have some O, and then there's a covering map, and the Pn acting on some connected hypersurface. Right. So this is what I'm saying is that if you have some horrible like this, with this sort of invariant on the gamma E, then it is actually the horrible R neighborhood. And actually, if you have this cone with the R removed, then it is actually lens cone. Okay, some Pn neighborhood. And so if you have some component of lens with remove with P and this acts properly and co-compactly and it acts on P, then it is actually the Tn neighborhood. Okay. So and then here I talk about the duality that uh, um, so if you have some Rn satisfying uniform middle eigenvalue condition, then the dual is a Tn with the uniform middle eigenvalue condition and the correspondence of the hyperplane here. And next, so if you have some n fundamentally satisfying uniform middle eigenvalue condition, and then the C is some lens neighborhood with the lens P neighborhood, then yeah, so the uniform middle eigenvalue condition for TPN structure is same as having a lens here. So we did it for the lens cone for Rn, but now we can do it for the Tn as well. So that's what this is saying. Okay, and the proof is just the duality argument here. And then the next, so if you have O and then O star, which is dual, then there's a correspondence of a Pn with the of O with the Pn of O tilde star by the Binberg diffeomorphism, and also these augmented Binberg duality will send Pn vertex to the n vertex of the dual Pn for the horospherical case. Okay, it's horospherical. So if not, for the Rn goes to correspond to Tn's. Okay, and of course this will send this Rn has a vertex will have right. So let me just skip this part. This is technical, and of course there's a correspondence between lens-shaped TPN and the lens-shaped RPN, and the ideal boundary component of TPN is projectively diffeomorphic to the projective convex domain dual to the this is for the RPN. So RPN has a linking projective structure, so their structures are also dual to each other. Okay, so that's again what's happening. So again, you have to follow through what the duality means and so on. Okay, so finally, probably 5.57 is that so the structures of R and Tn's of the ends of O and O dual of O has a correspondence between the generalized lens shape with the lens shape T end and horospherical lens to themselves. And if it satisfies the triangle condition or every end is partially factorizable, then you can actually do it for the lens shape and the lens shape T ends and horospherical ends to themselves. Okay, because general lens may not always be the lens in some cases. Okay, so that's why we don't have that. Okay, and then finally here, so if you have any lens shape case, then you can always assume that the upper boundary component is tangent to the radial rays. That's because you can, so if you have any lens, then you can put it to the TP ends, and then from there, if you obtain back the lens, then it's always the case that these lens is always dual. It has this property of the tangency. Okay. So that's why this happens here. Okay, so that's the content for today, actually. Okay.